Hi friends, welcome to another session of Smart Crack NEET 2022 series, and in this session we are going to talk about the electric potential and capacitance. Okay, so this will be a one shot lecture on electric potential and capacitance. So let's begin. So what is an electric potential? So electric potential is defined as the amount of work required to be done to bring a unit charge from infinity and keeping it at some point, okay, in an electric field. So the amount of work done per unit charge to move a charge from infinity to a point in an electric field is the electric potential. Okay, then what would be potential difference? So let's say you have these 2 points, point A and point B, and you want to find out the potential difference between these 2 points. Okay, so there will be some potential at A, there will be some potential at B. So you take some charge, let's say Q naught, okay, it is known as test charge. So you move it from this point A to the point B, okay. Then there will be some work done to move it from point A to B. So it is WAB, let's say. So then that work done divided by the charge, okay, work done per unit charge to move it from A to B is equal to potential at B, that is final potential, minus potential at A, which is initial potential. Okay, the potential difference between 2 points is given as what? The potential at final point minus potential at initial point, and it is the work done to move a unit charge from first point or the initial point to the final point. Okay, then if you take this Q naught on the other side, then you can write work done to move a charge from point A to B is equal to the potential difference between those 2 points, okay, multiplied by the charge that you are moving. All right, then let's talk about the potential due to a point charge. Okay, so potential due to a point charge. So now let's say you have this point charge Q at some point in the space, and you bring some other charge from infinity and you keep it at distance r away from this charge Q. Okay, so there will be some work done in bringing that other charge from infinity, okay, and keeping it over here. So that work done is suppose the integral of minus f bar dot dr bar. Okay, so what is this minus f bar dot dr bar? So it is work done against the electric field of this charge. All right. So since it is work done against the electric field of this charge, we have this negative sign. Okay, so there will be some force due to this charge on the other charge that you are bringing in. So that force is F bar, okay, and dr is the infinitesimal small displacement. Okay, so this is equal to, if you substitute F is equal to Q into E, because E is equal to what? Force per unit charge. So force is equal to Q, the charge that you are bringing, okay, it is Q naught multiplied by the electric field on that charge, okay, electric field at position of that charge due to this charge, which is E. Okay, so if we solve this all, what do we get? We get the work done to bring a charge from infinity and to keep it over here, okay, it's equal to 1 over 4 pi epsilon naught multiplied by Q, this charge Q multiplied by Q naught, the charge you are bringing in, divided by R. Okay, so the distance at which you are keeping that charge. So the potential due to this charge is defined as work done to bring the other charge, okay, from infinity to R divided by Q naught, the charge that you are bringing. Okay, so VR, the potential due to this charge at distance R, it should only depend on this charge and not the other charge, right? So it is work done divided by that other charge that you are bringing in. So it cancels out with this Q naught in the numerator. Okay, this Q naught in the denominator will cancel out with, if we take formula for work done, it will cancel out with this Q naught with the in the numerator, and we'll get this formula. So this is potential due to a point charge. Okay, after that, so this formula we need to remember, 1 over 4 pi epsilon naught into Q upon R. So similarly, we can have a dipole, okay, so positive charge separated by a negative charge. Same amount of negative charge by some distance is known as dipole. We know this well. Okay, so this is a positive charge plus q separated by some distance 2a from minus q. Okay, and we want to find out the potential of this system now at this point P. Okay, so what is significance of this point? So this point is at some distance r away from the center of the dipole, and if you draw a line joining the center of the dipole with this point, it makes an angle theta with the axis of the dipole. Okay, so P equals to Q times 2a is the electric dipole moment of the dipole. We have studied this in last chapter also, and we have studied it well in our 12th standard. So P equals to Q into 2a, and then the potential due to this dipole at this point is given by this formula. It is 1 over 4 pi epsilon naught multiplied by P cos theta upon r square. Okay, 1 over 4 pi epsilon naught into P cos theta over r square. All right. So now there are two particular points of importance. One is the axial point. So for an axial point, theta will be equal to 0. That means if we are taking any point on this axis, for it theta will be equal to 0, and then the formula for potential is given by 1 over 4 pi epsilon naught into P over r square. Okay, see, if you put theta equals to 0, cos of theta will be equal to what? 1. Cos of 0 is 1, and you get this formula 1 over 4 pi epsilon naught multiplied by P over r square. And then when the point lies on the equator of the dipole, if point is on equator, okay, equatorial line, a line which is perpendicular to the dipole and passing through its center. Okay, so if you take the point anywhere on the equator, then theta will be equal to what? 90 degrees, because angle between axis and the equator is 90 degrees. So cos of 90 is 0, and therefore potential at any equatorial point will be equal to what? 0, because cos of 90 is 0. Okay, so potential will be equal to 0. All right, so this is potential due to dipole at an axial point, 1 over 4 pi epsilon naught into P over r square, and this is on the equatorial point. Okay, very simple. After that, you want to find out potential due to a system of charges. What is that? Okay, so potential is work done per unit charge, so it's a scalar quantity. Okay, so it adds in scalar way. So potential due to n number of charges at a point. Okay, so let's say this point P is at distance r1 from q1, it is at distance r2 from q2, it is at distance r3 from q3, so on and so forth. There are n charges. Then potential due to all those n charges, it is just potential due to first charge plus potential due to second charge plus so on and so forth up to potential due to the nth charge. Okay, and then that potential can be given as 1 over 4 pi epsilon naught into, we can write it in this compact form, summation of qi upon ri. Qi is the ith charge and ri is the distance of that point from the ith charge. Okay, and the summation goes from I equals to 1 to n. Okay, after that, next is equipotential surface, the surface over which potential is equal, potential is constant. Okay, so a surface for which electric potential is constant is known as an equipotential surface, and this is of very high importance. Okay, the equipotential surface is very significant. So the work done to move a charge on an equipotential surface is 0. So if you move a charge from one point to the another point on an equipotential surface, there is no work done. All right, since there is no change in potential. As we have seen, work done to move a charge from point A to point B. Okay, let's say these are 2 points on an equipotential surface. So it is delta V, the potential difference between those 2 points multiplied by the charge. And for an equipotential surface, this potential difference is equal to 0. Okay, and therefore work done is equal to 0. It is simple. Then there is some relation between the electric field and an equipotential surface. So what is that relation? So, and there is some relation between the electric field and potential in some region also. Okay, so it comes from actually the two things are linked. Okay, so let's say we have these two equipotential surfaces. Potential of this first surface is V1, potential of the second surface is V2. V1 is greater than V2. Okay, then the electric field in this region is perpendicular to the equipotential surfaces. Okay, and the electric field is in direction of, let's say, which perpendicular. Okay, so there are two possible perpendiculars, one which goes from this surface to the surface 1 to surface 2, and one from surface 2 to surface 1. Okay, we can draw a perpendicular, right? So the electric field flows, or electric field is in the direction of from higher potential to lower potential. All right, so the direction of electric field is perpendicular to the equipotential surfaces, and it is directed from higher potential surface towards the lower potential surface. Okay, so this is the direction of electric field, and we write it in terms of formula like this. So electric field is negative of gradient of potential with respect to distance. Okay, so what is gradient? Gradient means derivative. Okay, so change in potential with respect to change in distance is the gradient, and we want negative of that. So this is for one dimensional case only. If we have, okay, let's say some region, and we want to find out the electric field, what do we do? So in that case, for the 3D case, the electric field is given by this formula, and this is the formula for gradient in 3 dimensions. So we'll have some formula for V, that is potential. So now it is negative of the derivative of potential with respect to x, and when we take derivative with respect to x, we'll treat y and z constants. Okay, so this symbol is for that. Okay, it says that when we are taking derivative with respect to x, we are treating y and z as constants, and this kind of derivative is known as partial derivative. Okay, so this is partial derivative of v with respect to x. Okay, so we'll get x component of electric field like this, the partial derivative of v with respect to x into I cap, plus y component as partial derivative of v with respect to y into j cap, plus partial derivative of v with respect to z into k cap. All right, so this is the z component. So we find electric field like this. Okay, so we'll see some examples on this, and then the next thing, so this is the relation between what, the equipotential surface and the electric field. All right, and the next thing is the potential energy. Okay, so what is potential energy of system of charges? So suppose you bring some charges from infinity and you keep them in some region, okay, in an electric field. So initially there might not be any electric field when you bring in first charge, then you bring other charges also. Okay, so the potential energy of the system of charges is the total work done against the electric field to assemble that system. Okay, to bring those charges from infinity and to keep them at some respective positions with respect to each other. And if we have two charges, then this potential energy is given by this formula. So we are keeping these two charges at distance of r12 from each other. So the potential energy is given by 1 over 4 pi epsilon naught into q1 q2 divided by r12. Okay, so simple. This is the potential energy. So after that, so we discussed potential in brief. After that, let's discuss capacitance. Okay, so chapter is electric potential and capacitance. So what is capacitance? So now let's say you have some conductor. For example, you have a spherical conductor and you are charging it. Okay, you're giving it some charge. So its potential will increase, right? So the potential is directly proportional to charge. For example, we have this formula V equals to 1 over 4 pi epsilon naught into Q over R. So potential is directly proportional to charge, or we can say charge is directly proportional to the potential. So if we remove the proportionality sign and put an equality sign, we know a constant will come in, and that constant here is known as the capacitance. Okay, so the constant here is known as capacitance. So capacitance will be equal to what? If you take this V on other side, capacitance is given by Q divided by V. Okay, and what is unit of the capacitance? Unit of capacitance is farad, and what is that? It is coulomb per volt. The unit of charge is coulomb, unit of volt is volt. Sorry, unit of potential is volts. Okay, so it is coulomb per volts. All right. So farad is the unit of capacitance, and it is given in the name of great Michael Faraday. Okay, who discovered many things in physics. And just uh, just to say, okay, he is my favorite physicist of all times. Okay, and I mean, okay, so let's move on. So the capacitance of, let's see the capacitance of some systems now. So capacitance of an isolated spherical conductor. So you have a spherical conductor like this. What would be the capacitance of that conductor? Okay, so the potential due to this conductor is 1 over 4 pi epsilon naught into Q over R. So you can see if you take this 4 pi epsilon naught R on the other side, you get Q equals to that 4 pi epsilon naught R multiplied by V, that is the constant times V, and therefore the capacitance of this conductor is what? That constant 4 pi epsilon naught R, right? So that is if you have air over there. If you have some medium, then the capacitance is given by 4 pi epsilon naught and the dielectric constant K for that medium K, okay, into R. Okay, so C is equal to 4 pi epsilon naught K times R. Is the dielectric it is the capacitance if you have some dielectric medium. Okay, after that, what is parallel? After that, next is parallel plate capacitor. So what is parallel plate capacitor? So if you have two plates, okay, two metal plates, and they are kept at some distance of, let's say, d from one another, then the parallel plate capacitor, it becomes the parallel plate capacitor. Okay, that system is known as parallel plate capacitor. So you can put some charge on one of the plates, let's say plus q, then some charge minus q is induced on the other plate, equal amount of charge is induced actually, okay, on this side of the other plate, and on the other side there will be plus q charge which you will remove, which you will ground it. Okay, so there is some charge and there is some potential difference now created due to this charge. Okay, so what is the capacitance? So the capacitance of this system is given by this formula. It is epsilon naught A divided by D. Okay, capacitance of parallel plate capacitor is epsilon naught A divided by D. All right. So this is if there is air in between these two plates. If you have some dielectric having dielectric constant K, then the capacitance is given by epsilon naught K into A divided by D. Okay, and after that, let's see combination of capacitors. So if you combine capacitors in series, so their capacitances are, let's say, C1, C2, C3, so on and so forth up to Cn. You combine them in series, what happens? So the resultant capacitance is suppose C, then the reciprocal of the resultant capacitance is equal to sum of reciprocals of all the individual capacitances. Okay, and if you combine them in parallel, then the net capacitance is suppose C, then it is just the sum of all the individual capacitances. Okay, so that is capacitance in series. So in series, the reciprocal of the resultant capacitance is equal to reciprocal of the total capacitance is equal to what? 1 over first capacitance plus 1 over second capacitance plus so on and so forth. Okay, up to 1 over nth capacitance. That is sum of all the individual capacitances. Sorry, sum of the reciprocals of all the individual capacitances will give you the reciprocal of the resultant capacitance. Okay, and for parallel combination, the net capacitance is suppose C, it is just sum of all the individual capacitances. Okay, After that, we have energy stored in a capacitor. So why would there be any energy? It's because you are charging a capacitor. So when you are charging it, there will be some energy stored into it, because if you put some charge, okay, let's say some positive charge, now you bring a little bit of positive charge, what will happen? There will be a repulsion between the original positive charge that is present over there and the charge that you are bringing. Okay, so now if you want to put that charge again on the capacitor, you have to overcome that resistance, you have to overcome the repulsive force between the charge which is already present there and charge that you are bringing in. Okay, so for that you have to put some energy, and that energy gets stored as the potential energy of capacitor. And what's formula for that? It is half of C into V square. Okay, this is one formula. Then there is another formula. If you use the relation C is equal to Q upon V, you can find out this formula. It is half of Q into V, and also this formula, half of Q square divided by C. Okay, so that's potential energy of a capacitor. After that, let's talk about the capacitors connected to each other. So if you have two capacitors, okay, with capacitances C1 and C2, and you are connecting them like this. So if you connect the plates with same polarity, okay, so positively charged plate with positively charged plate and negatively charged plate with the negatively charged plate, then the potential difference between them now, because you are connecting them in parallel, and we know in parallel combination potential is same, potential is equal. So potential between them will be C1V1 plus C2V2 divided by C1 plus C2. Okay, this is the formula. And if you connect the plates with reverse polarity, opposite polarity, with each other, then what will happen? So you are connecting positive with negative of first one and second one, and vice versa. Then you will get what? V equals to the potential difference between them is C1V1 minus C2V2 divided by C1 plus C2. Okay, all right. And in doing so, there will be some loss in the energy of the system, and that loss in energy is given by this formula. It is half of C1 C2 multiplied by V1 minus V2 square divided by C1 plus C2. Okay, so if you like, you can memorize this formula too, but please memorize this formula: C1 V1 plus C2 V2 divided by C1 plus C2 if plates with same polarity are connected to each other, and C1V1 minus C2V2 divided by C1 plus C2 if plates with the opposite polarity are connected to each other. Right. So this is all there in the theory of electric potential and capacitance that we need to remember to be able to solve the problems. Okay. And now let's solve some problems based upon this. So problem 1. In the region of space with volume, this is the volume, the electric potential is found to be 5V throughout. Okay, so given is electric potential equals to 5 volts. Then the magnitude of electric field, we want to find out the magnitude of electric field. The potential is this much. Okay, so we saw the electric field is given by what? Minus of dV by dr. All right, so it is change in potential with respect to the distance, and here the potential is constant, right? There is no change in potential, it is 5 volt throughout. Okay, therefore since there is no change in potential, the electric field will be 0. The option A. All right, this is simple. Then the electric potential at a point in t space due to charge q coulomb is this thing, the electric field at that point. So we are given with the formula for, sorry, not the formula, we are given the value of potential, and we want to find out the electric field in that region. So potential, we know it is due to a single charge. Potential is given by what? 1 over 4 pi epsilon naught into q or r, and it's given that this is equal to q into 10 raised to 11. Okay, so we can cancel out Q like this, and what do we get? So we get R equals to something. R equals to what? And yeah, we get, if we take R on this side, 10 raised to 11 on this side, we get R equals to 1 over 4 pi epsilon naught into 10 raised to 11, right? After that, if we want, we can put value of 4 pi epsilon naught also. Okay, but we want to find out the electric field, so let's do that. Electric field is equal to what? 1 over 4 pi epsilon naught into Q over R square, or we can say it is V divided by R. All right, so let's substitute that. Let's substitute the formula for V is this, and there is R also. So V is given, it is Q into 10 raised to 11, and this R is what? It is 1 over this thing, 4 pi epsilon naught into Q, 10 raised to 11. So 10 raised to 11, no, this 10 raised to 11 will go into the numerator. So it will become what? 10 raised to 11 plus 11, that is 10 raised to 22. And this 4 pi epsilon naught also goes into numerator. So you get E equals to 4 pi epsilon naught into Q into 10 raised to 11 plus 11, that is 22. Okay, so option C is the answer, right? Simple, very, very simple, in fact. Let's move on to the next question. The next question is, a short electric dipole has a dipole moment of 16 into 10 raised to minus 9 centimeters. Okay, so dipole moment P is given for a dipole. It is 16 multiplied by 10 raised to minus 9 coulomb meters, not centimeters. Okay, the electric potential due to the dipole at a point at distance of 0.6 from the center of the dipole. Okay, so R, the center, the distance of that point from the center of dipole, it is how much? It is 0.6 meters, and it is situated on a line making an angle 60 degrees with the dipole axis. So this is dipole axis, and the point is at an angle of 60 degrees. Okay, so theta equals to 60, and what do we want? We want to find out electric potential, and it's given that 1 over 4 pi epsilon naught, 9 multiplied by 10 raised to 9. Even if it is not given, we know it, right? So we also know the formula for the electric potential due to dipole. It's 1 over 4 pi epsilon naught into P cos of theta over R square, right? So let's substitute values. So we get V equals to what? 1 over 4 pi epsilon naught is 9 into 10 raised to 9 multiplied by P cos theta. So P into cos of 60 degrees. Okay, I will write whatever I remember upon R square. Okay, upon R square. So it is 9 times 10 raised to 9. Cos of 60 is sine of 30. It is half multiplied by P. P is how much? 16 into 10 raised to minus 9. The 16 into 10 raised to minus 9 divided by R square. So R is 0.6. So 0.6 square we have. Okay. So 2, can we cancel it out? We can cancel it out with 16, and okay, 8 2s are 16, and then we have 0.6 square. So it is 9. This is 9 into 10 raised to, okay, one good thing is this 10 raised to 9 minus 9 gets cancelled out. So we have 9 multiplied by 8. Okay, this has got simplified. So this is 0.6, right? I can write it as 2 times 0.3, and 0.3 I can write as 3 into 10 raised to minus 1. Okay, and we have square of that, right? So 3 square is 9. I can cancel out with this 9, and 2 square is 4. Okay, so 8 upon 4 gives me 2, and this 10 raised to minus 1 I will, okay, 10 raised to minus 1 square, 10 raised to minus 2. Take it in numerator, it becomes 10 raised to plus 2. So we have 2 times 10 raised to plus 2 or 100. Okay, so 200 is the answer. Option B is the answer, right? Okay, this was very simple, very straightforward, and most of the questions from this chapter will be simple. All right. After that, next question: a conducting sphere of a radius r is given a charge q. The electric potential at this and the electric field at the center of the sphere respectively are. We want, okay, it's very simple. The electric potential and electric field at the center of the sphere. So we have a conducting sphere. Okay, so what will be potential due to the sphere at the center? This is the question. And also the electric field. So see, this is made up of conducting material. Okay, potential will be constant everywhere. All right, because if there is some charge, okay, and it's a conductor, charge can flow inside a conductor, right? So if there is some potential difference, so charge will keep on flowing, till the time there is some potential difference between any 2 points. Okay, and in the equilibrium, how will the charge will get distributed? So it gets distributed in such a way that the potential difference between any 2 points is zero, because if it is not zero, the charge will still keep on flowing. Okay, so potential over here is equal to how much? It is just equal to potential over here. Okay, that is at the boundary of that surface, or on the surface of that sphere, you can say. Okay, so it is q upon 4 pi epsilon naught r, or 1 upon 4 pi epsilon naught into q or r is the potential. And since, as I said, there won't be any potential difference between any 2 points of this charged sphere, so potential is constant everywhere. So if potential is constant, we have discussed there won't be any electric field. Okay, so electric field is 0 and potential is 1 over 4 pi epsilon naught q over r. Okay, so first is electric potential, second is electric field. So option B is the answer. All right, very simple, very straightforward. After that, next question is 4-point charges minus q, minus capital Q, minus small q, 2q, and 2 small q and 2q are placed one at each corner of a square. So we have a square and the charges are, they are kept one at each corner of this square. Okay, so charges are minus q, minus small q, then 2q and 2 capital Q. All right, so then the relation between capital Q and small q, this is the question, for which potential at the center of the square is 0. So potential at the center of the square is 0. Okay, so potential over here is 0. So we can say this point is at same distance from all the charges. It's the center of square, right? So let's call that distance r. And how much will be potential there? So V at the center, okay, V at center will be equal to what? 1 upon 4 pi epsilon naught or K, I will take outside, multiplied by minus Q or R plus this minus Q or R plus we have 2q or R, plus we have this capital 2q or R. So we add it up, what do we get? So it's given that it is equal to 0, okay, and 1 upon R also we can take common, so it's k upon R multiplied by whatever is there, so it is minus q plus 2q is q, and 2q minus q is small q, so q plus q, okay, and since q plus small q is equal to 0, because this thing is not, okay, if you take this on the other side, it's 0 divided by this thing k upon R, still 0, so q plus small q is 0, and therefore q should be equal to minus q minus small q, okay. So this is simple, very simple. 4 electric charges plus q and minus q are placed at the corners of a square of side 2l, so side is 2l, and the electric potential at point A, at this point midway between two charges plus q and plus q, is how much is the electric potential, that we have to find out. So see, this is of side 2l, so this distance is 2l, and if I join this with this point, okay, so this distance will be l, right? So now this distance is suppose r, okay, this distance is l. So how much is potential at this point A? So potential at A, let's call it VA, will be equal to 1 upon 4 pi epsilon naught, we can take it outside, into multiplied by this q upon this distance L, this q upon this distance which is L, so q upon L plus q upon L, plus it is what, minus q divided by this distance R. And what is R? So this is uh, what, this is right angle triangle, so we have r square equals to this side square plus this side square, and if we want r, it is square root of that this side square plus this side square, okay. So it is minus q divided by 2l square plus l square raised to half, and plus again we have minus q multiplied, sorry, minus q divided by this side, so it is minus q divided by, again length of this side will also be same, 2l 2l square plus l square raised to half, okay. And then we can do some, no cancellations, it is k into q plus q, 2q divided by l, plus we have minus q, okay, and in denominator this is 4l square plus l square, so it is 5l square, okay. So 5l square raised to half, so we can take a square root of l square, it is l, okay. So it is 5 root l, sorry, root 5l, this is also root 5l, so here if we add this thing also, we'll get what, so here it will be minus 2q, okay. So again we can take everything common, I guess, so it is VA, I mean by everything I mean 2ql we can take common, so k times 2q, that is 1 upon 4 pi epsilon naught times 2q, because in options it's 1 upon 4 pi epsilon naught, 2q or l multiplied by 1 from the first term, and from the second term it's minus of 1 over root 5, okay, 1 over root 5. So this is the answer. So option C is the answer, okay. Again this was very simple, nothing complicated. Let's move on to the next question. The diagrams below show region of equipotentials. Okay, and these are equipotential surfaces. This is first, second, third, fourth case, and potentials are 10 volt, 20 volt, 30 volt, 40 volt. 10 volt, 20 volt, 30 volt, 40 volt. Okay, I guess it is same for all diagrams. Okay, a positive charge is moved from A to B in each diagram. So you are moving a charge from A to B, that is from the 10 volt potential to 40 volt potential in each diagram. Then options are, in all the four cases the work done is same. Yeah, this is the answer, right? In all the four cases the work done is same. Okay, let's read other options too. The minimum work is required to move in figure, not exactly. Okay, so maximum work is required, again not possible. In figure B it's not possible because same work is required in all cases. Maximum work is required in figure 3, no. Okay, same work is required. Okay, it does not depend on distance or anything. It only depends on how much is the potential difference. Okay, so same work is done in all cases. Let's move on to the next problem. Next problem is, if potential in volts in region is expressed as this thing, okay, then the electric field at some point, electric field at a point is, so we know the relation between the electric field and potential. So electric field is what? It is minus of del V by del X into I cap del V. Okay, I will write it here only. Minus, or let's say minus of this plus del V by del Y. I have taken minus sign common, into J cap plus del V by del Z times K cap. So that is equal to minus of del by del X of this thing. Okay, this is the formula for V. Okay, so that is 6xy minus y plus 2yz. We have to take its derivative with respect to x. Then we have this thing into I cap plus del v by del y. So del by del y of 6xy minus y plus 2yz into j cap. Okay, is it going outside screen? No. Plus we have del by del z of 6xy minus y plus 2yz into k cap, and that's all. So let's take the derivatives. So minus of, so in first case we have to take derivative with respect to x, so we have to treat y and z as constant, so there won't be any derivative of this two terms. Okay, so in this two we have to take y as constant, so 6y we can take outside, and derivative of x with respect to x is 1. Okay, so it is 6y times I cap, right? What I have done, I have taken derivative of this term with respect to x, treating y and z as constants. Okay, so derivative of this term and this term will be 0, and here also you can take y as constant, you can take it outside of derivative, so 6y you will take out. Okay, and then you have to take derivative of this x with respect to x, that is 1. Okay, so it is minus of 6y only. Okay, so minus 6y into I cap, plus we have in bracket, we have derivative with respect to y. So here y is there in all terms, so we have to be a little bit careful. So here 6x is constant, we can take it outside, so it is 6x. Derivative of y with respect to y is 1, so 6x into 1, then minus dy by dy is 1. Okay, so minus 1, then we have plus 2z, it is plus 2z into dy by dy is 1. Okay, so this thing into j cap, and plus we have what? We have derivative with respect to z. So there is z in last term only. So for first two terms, derivative is 0. And in last term, 2y is constant. I can take it out. So it is 2y into dz by dz is 1. So it's 2y into k cap. Okay. Yes. So then we want this at point 110. Okay, so we want electric field. We found the formula for electric field in this region having the potential given by described by this formula. We want the electric field at point 110. Okay, so let's substitute the point 110. So for that, I will take this formula on the next page. Let's paste it. So this is the potential, sorry, this is the electric field, and we want it at 110. So x equal to 1, 110, right? X equal to 1, y equal to 1, z equal to 0. So let's substitute that. So E, we get 6 times 1 into I cap. So minus of 6 I cap. Then here it's plus 6 times 1. Okay, 1 minus 1 plus z is 0. So this is 0 j cap. Okay, so 0 is j cap and 2y. So it is plus 2 times y is 1. Okay, so 2 k cap. Okay, so minus 6 I cap plus 2 k cap should be the answer. It's not there. Did I miss something? It is 110. Oh, I missed this thing. It was 6 times x. Okay, so it is 6 times x. So this thing is 6. Okay, so yeah, it is minus 6i plus 6j. No, not 6. 6 minus 1, 5j plus 2k. So option D is the answer. Okay. All right. Let's move on to the next problem. In a region, the potential is represented by this thing. Okay. Again, we have similar problem where V is in volts and XYZ are in meters. The electric force experienced by a charge of 2 coulomb situated at point 111. So this is exactly similar to the last problem. We want to find out the electric force now. Okay, so first we have to find out the electric field. So let's do that. So E is given by what? This minus of dV del V by del X into I cap plus del V by del Y into J cap plus del V by del Z into K cap. Okay, and let's substitute V. So V is what? So it is given by this formula. Okay, it is 6x minus 8xy minus 8y plus 6yz into I cap. Then del by del y of the same thing, 6x minus 8xy minus 8y plus 6yz into k cap, and del by del z of the same thing, 6x minus 8xy minus 8y minus 6yz into, okay, sorry, it was del by del y into j cap, and here it is k cap. Okay, so this thing. So let's see. Okay, what do we get? So we get E bar equals to, minus sign is there, and I will write x, y, and z components. Okay, so it is, so here it's x is there in this term and this term and not in the other two terms. So it is 6 minus, because 6 I can take out, derivative of x with respect to x is 1. Okay, the 6 minus here 8y you can take out. okay, and derivative of x with respect to x is 1. So 6 minus 8y. So 6 minus 8y into I cap. We found x component. Then we have derivative with respect to y. So this term is 0 because x will treat it as constant. Then, okay, y is present in all the other terms. So here 8x we can take out. Okay, so derivative of y with respect to y is 1. So here we have minus 8x into derivative of y with respect to y, that's 1. Minus 8 into dy by dy is 1, and plus we have 6y, sorry 6z. 6z into dy by dy is 1. Okay, 6z into j cap. Not going out now? No. Then we have, okay, derivative with respect to z. So there is no z in this term, this term, this term, that's good. Derivative with respect to z in this term. So 6y we can take as constant. So it is minus 6y into k cap. Dz by dz is 1. So this is the electric field. And are we given with the point? Yes. So it is 1, 1, 1. So x, y, z is equal to 1. Okay. So let's copy this on to the next page. All right. And let's substitute x, y, z is equal to 1, 1, 1. So what do we get? So we get, it is minus of 6 minus 8 into I cap, because y is 1. Then plus we have minus 8, okay, minus 8 into 1, minus 8 plus 6 into j cap, plus we have minus 6 into y is 1. Okay, so minus 6 k cap, and that is equal to, okay, so it is 6 minus 8, so 2, that's minus 2, and this negative sign gives me plus 2. So 2i, then minus 8 minus 8 minus 16, minus 16 plus 6 is minus 10. Am I right? Yes. Minus 16 plus 6 minus 10, and this negative sign is plus 10 into j cap, plus we have minus 6 k cap and this negative sign, so it is plus 6 k cap. So this is the electric field. Okay, and we want force. Okay, so force, and we want magnitude of that, because, okay, there are no vectors in the options. Force acting on 2 coulomb charge. So let's multiply this with 2, because force is equal to what? It is q into e. Okay, so it's equal to 4, 2 times 2 into I cap, plus 2 times 10, that's 20, into j cap, plus 6 times 2, 12, to k cap newtons. And we want its magnitude. So F equals to square root of fx square plus fy square plus fz square. So that is 4 square plus 20 square plus 12 square, whatever it is. So it is 16 plus 20 square is 400, plus 12 square is 144. Okay, so 544 plus 16, so 560, I guess. Okay, square root of 560, and I don't know its square root. It will be somewhere over 20. Okay, of course it is less than, so I guess it would be around 24 or something. Okay, not 24. So let's do the reverse calculation. So 6 square is 36, 36, let's take it in the square root. Okay, so 36 multiplied by 5, is it 560? No. So that's not the possible case. It's definitely not this. 4 square is 16. 16, we'll take it inside. So 16 times 35. So 35 twos are 70. Oh, this is the answer. 4 square root of 35. Okay. So yes, 4 square is 16. So 16, I mean, this will be in square root. 16 times 35. So 35 times 16. Okay. So I can say it is 35 times 2 multiplied by 8. So 35 times 2 is 70. Okay, 70 times 8. So 8 sevens are how much? 56. Right. And we have 560. Okay, so that's the answer. So it is option D, 4 root 35. All right. So yeah, little bit of calculations, but otherwise simple question. Next question. A, B, C are 3 points in uniform electric field. The electric potential is, okay. So maximum at C, same at all 3 points A, B, C, maximum at A, maximum at B. So it is maximum at B, right? We have studied this, that electric field, it its direction is from higher potential to lower potential, right? So it's maximum at point B and it goes on decreasing. Okay, very simple. Next question. Charges plus Q and minus Q are placed at points A and B. These are points A and B respectively, which are at distance 2L apart. C is the midpoint between A and B. The work done in moving the charge plus Q along this semicircle CRD is, if this is simple, there will be some initial potential at this point. Okay, so our charge is initially over here and then finally we are keeping it at this point. So there is some potential due to the charges which are kept at these 2 points, plus Q and minus Q. So there is plus Q charge at this point, minus Q at this point. Okay, so let's find the potential at point C. So this is the initial point, this is the final point. So potential at C is equal to, okay, how much is laying? A and B are distance 2L apart. So this distance is L, this distance is L. Okay, and this is semicircle. That means this is the radius. So this distance is also L. Okay. So then we have V at point C equals to what? 1 over 4 pi epsilon naught K multiplied by this Q over R1, that's L, Q over L plus this Q over R1, okay, this Q over R, that is minus Q over L. Okay, so that is 0. Plus Q over L minus Q over L is 0. Okay, and let's find potential at D. So potential at point D is equal to some constant 1 over 4 pi epsilon naught into Q divided by this much, this much distance, which is 3L. So Q over 3L minus, not minus, plus minus Q over this, I'm sorry, this distance, L. So we can take Q over L common. So this is, I'm sorry, K into Q over L multiplied by 1 over 3, and here we have minus 1. Okay, so that should be minus 2 over 3. So we have VD equals to K, capital K, which is 1 over 4 pi epsilon naught into Q over L and minus 2 over 3. Minus 2 over 3. All right. So that is, we can write minus 2 over or not minus 2. We'll cancel this 2 with 4. So we are left with 2. So it is minus 1 over 2 times 3 is 6 pi epsilon naught into Q over L, that's Vd. And we want to find out the work done to move charge Q from this point to this point. Okay, so it is simple. So it is work done equals to final potential minus initial potential at point C multiplied by the charge. So that is minus 1 or 6 pi epsilon naught into Q over L. All right, very simple. Okay, so which option? Option C is the answer. Okay, so let's move on to the next question. Next question is, an electric dipole moment P is placed in an electric field of intensity E. The dipole acquires a position such that axis of the dipole makes an angle theta with the direction of the field. Assuming that the potential energy of dipole to be 0 when theta is 90 degrees, the torque and the potential energy of the dipole will respectively be. So if you know the formulae, this is also a direct question. Okay, so this is very, very simple. So what is torque acting on a dipole placed in an electric field? So this is, suppose, the dipole P bar, this is the electric field, angle between them is theta. Then we know the torque acting on the dipole is given by Pe sine theta. Okay, after that, now this torque will tend to rotate the dipole. Okay, and we suppose we exert some external torque of same magnitude and we rotate it. So the reference angle is given to be 90 degrees. So this is the initial angle and final angle is theta. Okay, so dipole acquires some position theta. All right, the final angle is theta. So there will be some work done, and that work done gets stored as the potential energy of this dipole. So let's find out that work done. So we know that dW, let's say, is work done to rotate it with an angle d theta. So it is tau into d theta, right? So work done will be, work done to rotate it from theta 1 to theta 2 will be integral of this dW, that is integral of tau into d theta from theta 1 to theta 2. Okay, so that is it will be, work done is integral from theta 1 to theta 2 of Pe sine of theta d theta, and P is constant, so we can take it outside of the integral. So what do we get? Pe multiplied by integral sine theta d theta from theta 1 to theta 2, and integral of sine theta is, we know it is cos theta, sorry, minus cos theta. So it is minus sine, I will take it outside, minus of Pe into cos of theta from theta 1 to theta 2. Now what is theta 1 and theta 2? So theta 1 is 90 degrees and theta 2 is equal to theta. Okay, so let's substitute that. So what do we get? It is minus Pe into cos of theta 2 minus cos theta 1. So cos of theta 2 minus cos of theta 1 is 90 degrees. So that is cos 90 is 0. Okay, so this term will not be there. So theta 2 is theta. Let's substitute that. We get minus of Pe into cos of theta. So this is the potential energy. So what is potential energy? Minus Pe cos theta. And what is the torque? It is Pe sine theta. So let's check the options. So minus Pe sine theta and Pe cos theta. Sorry, it should be Pe sine theta because torque is first and potential energy is second. So option A is the answer. Okay, so very simple. And I will just tell one more formula. Potential energy of a dipole at position theta. Okay, it is given by this formula: U is equal to minus of P bar dot E bar. So we have solved it here. Okay, so it is what? Minus P into E into cos of theta. Okay, so this is a direct formula to be memorized. All right. Okay, so let's move on to the next problem. An electric dipole moment P bar is lying on along the uniform electric field E. The work done in rotating the dipole by theta is, okay, so we have just found how much is work done. It is minus Pe into cos of theta 1, cos theta from theta 1 to theta 2. Okay, or we can say the work done, the work done is equal to minus Pe into cos of theta 2 minus cos theta 1. So let's substitute the values. So initially it is lying along the electric field, so angle is what? 0 degrees. Then the final angle is 90 degrees. So minus Pe into cos of 90 degrees minus cos 0. So cos 90 is 0, cos 0 is 1. So this is minus 1, minus 1 multiplied by this negative sign. Okay, so it is plus 1. So it is P times E. So that's work done. Okay, so option A is the answer. All right, let's move on to the next question. The electrostatic force between the metal plates of an isolated parallel plate capacitor C having a charge Q and area A is A, independent of the distance between plates, linearly proportional to the distance between plates, then proportional to the square root of the distance between plates, and inversely proportional to distance between the plates. Okay, so the electrostatic force between the metal plates of an isolated parallel plate capacitor, this is the question. Okay, so we have a parallel plate capacitor, so plus Q and minus Q. We want the force between these two metal plates. So does it depend on distance? Is it independent of distance? Is it inversely proportional to distance, etc., etc.? This is the question. And the answer is very simple. See, this is the second plate. So we can imagine this is charge minus Q kept in the field of plus first plate. Okay, in the electric field of first plate. So what is the electric field due to an infinite plate? So it is, we know it is sigma divided by 2 epsilon naught if there is air. Okay, so that is electric field due to first plate. So let's suppose it is an infinite plate. Okay, so electric field at any point will be sigma divided by 2 epsilon naught. And what will be force then? It is E multiplied by this charge minus Q. Okay, so sigma, which is charge upon area, charge on first plate divided by area, so Q upon A into epsilon multiplied by charge on the other plate is minus Q. Okay, so it does not depend on the distance. Okay, it does not depend on the distance, so it is independent of distance between two plates is the answer. All right, next question. A parallel plate air capacitor has capacity C. The distance of separation between plates is D and potential difference V is applied between the plates. The force of attraction between the plates of parallel plate air capacitor is. Okay, so yeah, force of attraction we have found it out. It is this thing, right? So just like that, we'll use that formula. It is Q square divided by 2A epsilon naught. Okay, so it is Q square divided by 2A epsilon naught. Okay, so then we can write Q equals to CV. Okay, so for a parallel plate capacitor, this force equals to Q square upon 2A epsilon naught. We'll find like this in this case, and we know Q is equal to CV. Okay, so we can substitute that. So it is C square V square divided by 2A epsilon naught, and uh, this is not there in options, so we have to substitute for A epsilon naught. Okay, so we know capacitance C is equal to what? It is epsilon naught A upon D. So epsilon naught A equals to CD. Okay, because if we take the D on other side, it will be CD. So if we substitute that, it is C square V square divided by 2 times CD, and this C gets cancelled out with this square, so it is CV square upon 2D. So this should be the answer. option option D is the answer. CV square upon 2D. Okay, very simple. All right, so let's see next problem. The capacitance of parallel plate capacitor with air as a medium is 6 microfarad, and with the introduction of dielectric medium, the capacitance becomes 30 microfarad. The permittivity of the medium is, this is very simple question. Okay, so capacitance with the dielectric is epsilon naught Ka upon D. Capacitance without dielectric, okay, if there is just air, it is epsilon naught A over D. So C due to C of a parallel plate capacitor, capacitance of parallel plate capacitor with dielectric is what? It is K times, we can say, K times C of a parallel plate capacitor with just air in between the two plates. Okay, so we want to find out the permittivity of the medium. Okay, so which will be epsilon naught K. All right, so before that we want to find out the value of K. So C divided by C air will give us K, and that is how much? It is 30 divided by 6, it is 5. Okay, and then we want permittivity or relative permittivity. Okay, permittivity we want, not dielectric constant. So it is this permittivity of the medium, epsilon is epsilon 0 K, and that is equal to what? 8.85 multiplied by 10 raised to minus 12 multiplied by 5. Okay, so 8 5s are 40, so 40 times 10 raised to minus 12, or 4 into 10 raised to minus 11, right, would be the answer. Or 0.44 into 10 raised to minus 12 minus 10. This should be the answer. Okay, very simple. After that, let's see this next question. Two thin dielectric slabs of dielectric constants K1 and K2 are inserted between the plates of a parallel plate capacitor. Okay, as shown in the figure. So these are dielectric slabs. The variation of electric field between the plates with the distance D as measured from plate P, okay, is correctly shown by. All right, so these are the diagram showing the electric field with respect to the distance, and here it's dielectric constant K1, here it is dielectric constant K2. So what do? So we know the formula for electric field, okay, between the capacitance, electric field of capacitor, it is what? It is given by sigma divided by epsilon, or epsilon 0 K. So if we have dielectric, then the electric field will reduce. Okay, and if dielectric constant is more, that means there is more reduction in the electric field. So it's given that K1 is lesser than K2. So electric field here will be more compared to electric field over here and here. Okay, electric field in the region of free space or air, it will be more compared to electric field where there is dielectric, right? So, and in that too, K2 is more than K1, so there the electric field will be least. So which are the, in which option that is true? So it is true for option C. Okay, see over here, the electric field is least in this region where we have, that region is filled with the dielectric, with dielectric constant K2. Okay, so it is least over here, and it is little bit less in this region also where we have put another dielectric with constant K1, and since K2 is greater than K1, it is lesser in this region. Okay, so option C is the answer. All right, then let's see the next problem. Three capacitors, each of capacitance C and breakdown voltage V are joined in series, so we are connecting them in series. Then the capacitance and breakdown voltage of the combination will be. So this is very simple question. So what will be capacitance in series combination? So these are three capacitors. So capacitance, net capacitance in series 1 upon C, let's say C resultant will be equal to what? 1 over C plus 1 over C plus 1 over C. Okay, that is 3 upon C. Okay, so 1 upon CR equals to 3 upon C. So the resultant capacitance is C divided by 3. Okay, so C divided by 3. And what about the potential difference? So potential difference, see, potential difference between these two plates is V. Between these two plates it is V, and between these two plates also it is V. Okay, so it is V plus V plus V. How much? It is 3 times V. So C by 3 and 3 times V should be the answer. Okay, so we saw the theory of electric potential and capacitance in brief, and we also solved some questions. So I hope you understood the questions and their solutions too, and you will solve some more questions, okay, based upon this chapter. So that's all for this lecture. See you in the next lecture. Thanks for watching.